Hi there, this is Raylene, and in this video we are going to take a look at squares, cubes, prime numbers, highest common factor, and lowest common multiple. So we'll start off by talking about a three-dimensional cube, and I will sketch a 3D cube by making a square and then copy-pasting it and filling it in to make a 3D effect. So we know that a cube is a three-dimensional figure with 6 faces or 6 surfaces, and each of those surfaces is a square. So the length of each side of the square, I'm just going to group that together, is the same distance, the same length. And so in this case we're told that the cube has a length of 5 centimeters, and every single length is 5 centimeters. So this is our labeled sketch. We could do things like put tick marks here to show that all the lengths are the same, but I don't want to do that and make the sketch too cluttered. Then in part B it says to determine the sum of all of the 1D lengths. So let's just really count carefully how many lengths we have. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of them. And so we're going to have the sum of all of the one-dimensional lengths is going to be a sum of 12 lengths, which is going to be 12 of 5 centimeters, or 12 times 5 centimeter lengths, which is 60 centimeters total. In part C, we want to determine the sum of all the areas of the 2D surfaces. So now we want to see how many surfaces we have. I'll color in a different color. We've got 1 on the bottom, and we've got 1 on the top. We've got 1 on the back, and we've got 1 on the front, and we have 1 on the side, and another on the side over here. So that's a total of 6. Now I think the coloring is a bit messy, so I'm going to actually uncolor it. But we counted 6 surfaces. Just imagine a die, or a pair of dice. Each die has 6 sides. So it's a sum of 6 areas now. And to find the area of one square, we take the length times the width. But in this case, they're both 5. So we multiply 5 times 5 to get the area. And so the sum of 6 areas is going to be 6 of, or 6 times, 25. But this time we're going to have a centimeter times a centimeter. So if we imagine a length of 1 centimeter, and then we create a square out of that, we create a new object. That new object is 1 centimeter times 1 centimeter, and we call it a square centimeter, or a square made out of 1 centimeter lengths. And so the unit for measuring area, if everything is measured in centimeters, will be the units of centimeters squared. And then we can use that idea of constructing a three-dimensional object. Again, if we take our 1 by 1 centimeter square and we make a 3D effect, we come up with a cube. Now this is a cube made out of 1 centimeter side lengths, and so the volume of the inside is called 1 cubic centimeter, or 1 centimeter cubed. So we want to know how many of these building blocks would fit inside of this 5 by 5 by 5 3D cube. So you might actually imagine a Rubik's Cube, which is very similar, but it's a 3 by 3 by 3 cube. So in this case, the volume is going to be what we get when we multiply the length times the width times the height, but in this case all of the lengths are 5 centimeters, and so we're going to get 5 centimeters times 5 centimeters times 5 centimeters, which is just 5 centimeters all cubed. And so 5 centimeters cubed is going to give us 5 cubed of centimeters cubed, because the exponent applies to both the 5 and the centimeters, and 5 times 5 times 5 is 125. So 125 of those individual centimeter cube building blocks would fit inside of here. Okay, in the next question, we just want to recall the perfect squares and the perfect cubes. So hopefully we know these and we're getting more familiar with them. 5 squared, or 5 times 5 is 25. So just fill these in. Memorizing them and knowing them by heart will make working with all of the numbers in this course a lot easier. Now there are some number patterns that we can remember. So there's lots of ways that you can practice these. So I like to memorize up to 25 squared, but I ran out of room on this space, so I left it to 20 for here. And then the perfect cubes, that would be things like 1 times 1 times 1, 2 times 2 times 2, 3 times 3 times 3, 4 times 4 times 4, and so on. Now let's say we don't remember one, but we know that 7 cubed is actually 7 squared times 7. So we had the 7 squared was 49 already, and then we multiply by 7. And then we can use a model to multiply this. I'm actually going to make it 7 times 7, 49, and then I'm going to put 7 down the side of a rectangle and 49 across the width. And so doing this, I could work out what 7 times 49 is, but 49 I can make it 40 plus 9. So I know that 7 times 4 is 28, so 7 times 40 is 280, and I know 7 times 9 is 63. Adding those two together gives me 343. So I could take 8 times 64, which would be 8 times 8 squared, and give a total of 8 cubed. And so doing that, 64 times 8 would be 8 cubed. But I know that 64 is 2 times 2 times 2, 6 copies, and I know that 8 is 3 copies of 2 all multiplied together, which is 6 copies plus 3 copies, which is a total of 9 copies of 2 all added together. If I know my powers of 2, I know that this number is 512. So there are other ways that I can combine numbers to work them out. 9 cubed, for example, is 9 times 81. And I know that 81 is 80 plus 1, so I could write it like that. And I know that this says I have 9 of 80 plus 9 of 1. So I could do 9 times 80 plus 9 times 1, which gives me 720 plus 9, which is 729. And then 10 times 10 times 10 is 1,000. So we can play around with different ways of combining numbers to multiply them. Number 3 says to determine the first and fourth consecutive, which means in a row, perfect square numbers, like the numbers up here, given the second and the third perfect square numbers. There's a small typo here. This should be a plus 9, so let's just make that change. And we have to recognize something about the blue numbers up here. These are the perfect square numbers. We know that to go from 1 to get to 4, it's going to get quite messy, but I'll just put it like this. We add 3, and then to go from 4 to get to 9, we add 5, and then we add 7, and we can explore this pattern of numbers, the sequence, and we see that every time the number that we add increases by 2. Then we would add 13, we would add 15, 17, 19, 21. So 121 minus 100 is 21. So if we add 21 to get from the 100 to the 121, then the next number we add to 121 would be 23. And we can confirm that 121 plus 23 is equal to 144, which is the next consecutive perfect square number. So if we added from this number to get 9, we must be going from 16 to 25. And that means that the next perfect square we would have to add 11, which would give us the 36 that we see here, and the number before that we would have had to have added 7, so that number would have been the 9. So this is just recognizing this specific number patterning for the perfect square numbers. In number 4, we are asked to write the numbers in standard form and use the box method for multiplying to show our working out. So in part A, we have 11 cubed. Standard form in this case is just asking us to expand it out, to write it not in factored or base and exponent form. Well, we know that 11 times 11 is 121 because that's 11 squared. And so now we want to work out 11 times 121. There are a couple of ways we could do this. And the box method says we could use a height of 11. I like to put the height for the first number in a product and 121 for the second number. Then I can break up the height into 10 plus 1. So I can break up the box into 2 rows. And I can break up 121 into lots of ways. I could break it up into 100 and then 20 and then 1, for example. So this would actually break up the big blue box into 1, 2, 3, 4, 5, 6 other boxes. There are other ways we could do it, but I like using all of the numbers that end in 0 where I can. So the first box has an area or a product of 10 times 100, which is 1,000. Working across the top, then I have 10 times 20, which gives me 200, and then 10 times 1, which gives 10. So the area of the top row is going to be 1,210. Then for the second row, I have a height of 1 times a base of 100, and so 1 times 100 is 100. Then I have 1 times 20, which is 20, and 1 times 1, which is 1. So the total area, or the total value of 11 cubed, is going to be the sum of all of those numbers. So 1,000 plus 200 plus 10 plus 100 plus 20, and then plus 1. And that final answer is equal to 1,331. In part B, we don't always have to use the box method. Here we have 2 cubed times 3 squared, and just to be really clear, the small number is the exponent, and it tells us how many copies of the base number we have joined together in multiplication. So we have 3 copies of 2, and then we have 2 copies of 3. The 3's and the 2's are joined by multiplication, and this means that all the 3's were joined by multiplication as well. So we could just multiply in order. 2 times 2 is 4, times 2 is 8, times 3 is 24, times 3. Maybe that's not so easy. So I'm going to encourage, when the operation is the same operation in the entire expression, that you group numbers in a way that makes the multiplication easy for you. So here I'm going to group 2 times the green product, which is 6, and then times the red product, which is another 6. And then from here, I know that 6 times 6 is 6 squared, or 36, and I can double 36 to get 2 30s is 60, and 2 6s is 12, so that gives me 60 plus 12, which gives me 72. Now you don't have to show this line. This is just for another way to hold the calculation in your head. So we're going to do something similar for part C. We have 2 to the 4 times 5 cubed. And again, you don't have to expand this out, but doing so helps me to come up with groupings that would be easy for me, and maybe you have a different grouping for you. So 2 times 2 times 2 times 2, and we have 3 copies of 5, all joined by multiplication. I know that 2 times 5 is 10, so I want to come up with some groupings of 2 times 5. And I have a green one, I have a red one, and a purple one. So this for me is the easiest, and probably for a lot of people is the easiest. 2 times 5 is 10, another 2 times 5 is 10, and a green 2 times 5 is 10. And 10 times 10 times 10 is 1,000, and 2 times 1,000 is 2,000. It might be difficult otherwise, because if you had just worked out the 2 to the 4, that's going to be 16, and if you work out 5 cubed, that's 125, and it might be harder for you to multiply 16 times 125 to get 2,000. But it would be interesting to know that if you have 16 times 125, if you break it apart and then regroup the factors, you could come up with the answer without a calculator in a very clever, creative, and efficient way. Let's do the same step for part D, which has 1, 2, 3, 4 different bases, 2 cubed times 3 squared times 5, and then times 7. So I know I would like to group a 2 and a 5 together, so I'm going to take 1 2 and 1 5 and make 10. Then I'm going to have 2 2's left and 2 3's left. So just like over here, I'm going to make a 6 out of each of those pairs. I've used the 5, I've used both of the 3's, I have now used all of the 2's, and I just have a 7 left. Now I'm going to reserve multiplying by 10 because it's easy to multiply by 10 once I have the rest of the numbers in. I can just put a 0 at the end of whatever 6 times 7 is. So now the question is, do I want to group 6 times 6 and then times 7, or 6 times 7 and then times 6? We know 6 times 6 is 36, so this might be helpful. And then we're going to multiply by 7 and then by 10. So we need to work this out. And in this case, I'm probably going to use a box method again. So I'm going to take 36 times 7, and I'm going to write it as 7 times 36. The only reason is I like my first number to be the height of the box, and my second number to be the base of the box. And my base is longer, and I don't have that much room left, so I want it to be wider than tall. So I'm going to put 7 here, and I'm going to break apart the 36 as 30 plus 6. So unlike here where I had 6 different boxes that I had to add together, here were the 6 different boxes. Here I need to find 2. So 7 times 3 is 21, so 7 times 30 is 210. And 7 times 6 is 42, So 210 plus 42, because I'm adding up the red amount of area and the green amount of area to get the total area of the blue box. So I now know that 36 times 7 is the sum of these, which is 252, and then multiply by 10 gives 2,520. Number 5 talks about the square root and the cube root of numbers. A root refers to the foundation or the basis or the beginning of something, like the root of a tree is what the tree grows from. So if we're thinking about the root or foundation of a square, we're talking about the length of a square. Similarly, the root of a cube refers to the root or foundation or the length of a cube. So I'm going to come up with a meaning, a picture meaning, a geometry meaning of each of these numbers. For part A, the square root, well, as soon as we say square or square root, we can visualize a square. And as soon as we see cube or cube root, we can visualize a cube. And I'm going to draw my cube as a 3D effect. By copying and pasting, you can try to mimic this picture on paper without copy pasting. And in this particular case, I want to find what the length is, and I'm giving the square root of 25 as the length. So the length is equal to square root of 25, which simplifies to 5. So we have a length of 5 and a length of 5. And the meaning of the 25 then, which is 5 squared, is the area of the square. So I'm going to put L for length equals, and I'm going to put area equals 25. Similarly over here, the cube root of 27, I'd actually like to change this to the cube root of 125 just for some consistency with the numbers. So the cube root of 125 is the length of a cube. And so the length is whatever number multiplies by itself 3 times to get 125. And we saw earlier that number is 5 when we did the table of values. And so the meaning of the 125 in this case is not going to be area, because it's going to be 5 for the length, 5 for the width, and 5 for the, let's see, 1, 2, and 5 along here. And so we would be fitting some building block cubes, each of which are 1 cubic centimeter. So we would have 125 of those, and this represents, that's equal to 5 cubed, and it represents the volume, the amount of space inside. And so I'm just going to use a different color, and I'll say inside that the volume equals 125. So we're just trying to look at numbers as having some concrete meaning from geometry. In this question, we're going to look at the factor pairs, the number of factors, and the prime factorization for each number. So start off by finding any way that you can factor the given number. So 32, we may start off as 4 times 8. And we're going to create a factor tree until all of the factors, which are numbers joined by multiplication, are prime numbers. Now remember, 1 is not a prime number. Our prime numbers start at 2, 3, 5, 7, etc. And prime numbers have only itself and 1, so 2 different factors, 1 and itself, as factors. Now the 4 can still be factorized, and so I'm going to break that apart as 2 times 2, and then each of the other 2's I'm just going to give a single branch in this factor tree. And so altogether we have 5 copies of 2, which multiply together to give 32. So that actually is our prime factorization. To come up with the factor pairs, we want to redistribute the numbers in different combinations to come up with different pairs of 2 numbers that multiply together. So I'm just going to do another diagram. I maybe call this a circle of factors diagram, and I'm going to start with 1 times something, 2 times something, 3 times something, 4 times something, 5 times something, 6 times something, and see how far along we can go. Maybe this isn't a great circle, but you can make it a bit more circular if you like. Well, we know that 1 times the number itself will always work, so that's going to be one of our factor pairs. Now we know that 2 over here is already a factor, so 2 multiplies by all of this, which is 16. And so 2 times 16 is another factor pair. And we're going to keep repeating this process for any numbers that we can. we see that 3 is not one of the prime number factors, so this is not going to be a possibility. 3 times nothing. This is not a factor pair for 32. In order to get 4, we could group two 2's together in multiplication, and 4 would then be multiplied by 8. And so we have another factor pair of 4 times 8. Now that one should not come as a surprise, because that's the one we started when we initially broke down the 32 into its factors in the first place. 32 ends in a 2, so it's an even number and is a multiple of 2. But in order to be a multiple of 5, any number has to end in 0 or 5. So right away we know that 5 is not a multiple and we do not have a factor pair here. We can take a look at 6, which is 2 times 3, and while we have a factor of 2 here, we don't have a factor of 3, so there's no way we can make a factor of 6. So 6 is not a factor of 32, and we don't have a factor pair here. Well, I went in order, 1, 2, 3, 4, 5, 6. We could try 7. 7 is a prime number, and we have all of the prime factors of 32 here, but there is no 7. So 7 is not a factor pair. The next number we could come up with is 8, and we see that, again, we're going in order, 1, 2, 3, 4, 5, 6, 7, 8. And 8 would be 2 times 2 times 2, and that would be multiplied by 4. So 8 times 4 is a factor pair, but we'll notice that we already had 4 times 8, so this is a repeat, so we don't count it twice. So now we can count up the number of factor pairs, we can count up the number of different factors, and we can state the prime factorization. So to answer part 1, the factor pairs, I'm going to write it like this. 32 is equal to 1 times 32. It's equal to 2 times 16. I'm going to put an equal sign in between because all of these results are equal to each other. 2 times 16 and equal to 4 times 8. So we have 1, 2, 3 different factor pairs, and the number of factors, we just count all the different numbers that we have. 1, 2, 3, 4, 5, 6. So we have 6 factors, and then in part 3, the prime factorization is that 32 is equal to 2 times 2 times 2 times 2 times 2, 5 copies of that, or you could write it as 2 to the exponent 5. I like this notation because it uses less ink, so it's simpler. Okay, we're going to do that for 105, 360, and 896 as well. To start factoring 105, notice that 105 ends in the digit 5. So 5 is a factor, and that means we can divide 5 into 105 evenly. So 5 goes into 10 2 times, and then 5 goes into 5 1 time. So we now know that 105 is equal to 5 times 21, with no remainder. 5 is prime, so I'm just going to write that down, and 21 can be factored into a product of 2 primes, 3 times 7. Then we can look at grouping that to get different combinations of 105. So first of all, we know 1 times 105 is going to be a factor pair. 105 is not even, and we don't have a factor of 2 here, so we're not going to have any 2 times, 4 times, 6 times, 8 times as a factor pair. So around my circle, I might just skip all of those. 3 times will work because we have 3 times whatever 5 times 7 is. And that's 35. 4 times something won't work. As I said, 4 is even, and we didn't have a factor of 2 because 105 is an odd number. We know that 5 is a factor. We've already found that 5 multiplies by 21. We won't have 6 because 6 is an even number, and we don't have a factor of 2 in this odd number. Then the next odd number is also a prime number 7, and 7 multiplies by 3 times 15. Sorry, 3 times 5, which is 15. And then 8 won't work. 9, if we want to see if 9 works, we might consider that 9 is 3 times 3, but we have one 3, but not another 3 as a factor. So we can't get a 9 as a factor, and this won't work. 8 won't work because 8 is an even number. Sorry, we did 8, 9. 10 won't work because 10 is an even number. 11 times something, well, we know that 11 is a prime number, but it's not one of the ones we have, so it won't work. And we can see that there's no other combinations we can come up with here because the numbers are already combined. So now we've got all of our different factors. Actually, I don't like that explanation. I'm going to do it a slightly different way. Let's keep going so that we can be absolutely crystal clear we've got all the factors. So we now know that 11 doesn't work, 12 won't work because 12 is an even number. 13, we could try that. 13 times something, but 13 is prime and it's not one of our factors here, so it doesn't work. We know that 14 won't work because 14 is even. Now I skipped putting some of these, 6 and 8 and 10. I didn't put those trials in. And then after 14 comes the number 15, and 15 is not a factor here, but 15 is 3 times 5. So we can make this 15 out of 3 times 5, and we know that 15 will multiply by 7. But we notice now that 15 times 7 is a repeat of 7 times 15. So we've kind of doubled back around ourselves, and now we know that we don't have to go any further. So we have 1, 2, 3, 4 factor pairs, and we can state them for part 1. So part 1, the factor pairs say that 105 is equal to 1 times 105, which is also equal to 3 times 35, which is also equal to 5 times 21, and also equal to 7 times 15. So I'm just going to move this over a little bit. I like the factor tree into the prime factorization, and I like the factor circle. It helps me to see all the different factor information that I need. So 7 times 15 is my last one. Then the number of factors that we have, don't count any duplicate factors, but we don't have any repeated here. So 1, 2, 3, 4, 5, 6, 7, 8 factors. We have 8 factors for 105, and then the prime factorization, we know that 105 is equal to a product of 1, 2, 3 prime numbers, and I like to put my factors in increasing order where possible. Okay, let's repeat that for the next question, for the next number, 360. So 360, we want to break it apart into any 2 factors we know. Since this ends in a 10, we know that 10 is a factor and 36 is the other factor. So keep factoring these numbers until you get all prime numbers. There's a couple of ways we could factor 36. Maybe you see it as 2 times something, or 3 times something, or 4 or 6. However you see it, break it down. 36 is a special number because it's a perfect square, so you might recognize 36 is 6 times 6. Now 2 is prime and 5 is prime, but the 6's are not prime, so we have to factor that into prime numbers. And here we start to see repeats of numbers, so I'm actually just going to reorganize this so that the smallest numbers are first. 1, 2, 3 2's together, 2 3's together, and 1 5 all together. Okay, so let's do our factor circle, and maybe I start here. 1 times 360, 2 times something is going to work, so we can circle that too and here, and we can get that the other number is whatever this is. You might also just divide 360 by 2, or you could multiply all of these green numbers, and you end up getting 180. So we're just going to go around like this until we have doubled back on ourselves. So the next pair might start with 1, 2, then 3, and we have a factor of 3 here by itself, so then we can come up with the resulting product. I'll just put it in a green loop. Or we could take 360 and divide it by 3. Either way, the green product is going to be 120. So 3 times 120, and then we come on to 4. 4 is equal to 2 2's multiplied together, and then the resulting factor is everything in here. 2 times 5 is 10, and 3 times 3 is 9, so 9 times 10 is 90. Alternatively, you could say 360 divided by 4, and maybe you just do 36 divided by 4, which is 9, so 360 divided by 4 is 90. Then we look for 1, 2, 3, 4, 5, and 5 will multiply in because we have a number ending in 0, and we have a 5 factor here, and the rest of the factors will be whatever this product is. So we're going to get 2 times 2 times 2, which is 8, times 3, which is 9, which is 72. It's nice to know our single-digit times tables so that we can do multiplications quickly. So far we haven't run out of a number, and we're not going to stop here. 6 occurs as a 2 times a 3, and then we're going to have a 2 times a 5, which is 10, times 2 times 3, which is 6, and 6 times 10 is 60. So we have 6 times 60. Alternatively, dividing 6 into 360 gives us 60. And then we go 1, 2, 3, 4, 5, 6, 7. 7 does not appear. 7's a prime factor, so we can't combine two numbers, say 3 times 5, or 3 times 3, or 3 times 2, or 2 times 2 to get 7. So we found our first missing factor number. Then we come along and we get 8, which we know is going to be 4 times 2, or 2 cubed. So that is our 8, and we're left with this number, which is 9 times 5, or 45. So 8 times 45 is 360. 9 we know is 3 times 3, which we have here. And then the remaining factors we have a 4 times a 10, which is 40. And that kind of is a slight bit of a swap around here. So 9 times 40 is another factor. After 9 comes 10, and we can make the composite number 10 by multiplying a 2 times a 5. That gives us this 10. And then everything else is the other factor. And we see that we've got 2 times 3 and another 2 times 3, which is 6 times 6, or 6 squared, which is 36. So 10 times 36 shouldn't be a shock because that was our easy one to get started. So don't lose sight of the easy ways of doing things just because we've started one way. 11 times something. 11 is prime, and it's not one of our factors, so we can't combine two prime numbers and multiply them to get this prime number, so we have another missing factor. After 11, we have 12, and 12 is 3 times 4, and 3 times 4 is 3 times 2 times 2. So the missing factor is going to be 2 times 3 times 5, and I want to group the 2 times 5, which is 10, times 3 is 30. Or I could do 2 times 3 is 6, and 6 times 5 is 30. So we have 12 times 30. And then we have another prime number, 13, which doesn't appear here, so there is no factor pair for 13. We didn't have a factor pair for 7, and 14 is 7 times 2, or 2 times 7. So since we didn't have a factor pair here, we won't have a factor pair here. There is no 7 as a building block. After 14 comes 15. I hope I'm out of factor pairs soon. I'm running out of room. 15 is made up of a 3 times a 5, and so the remaining is going to be 2 times 2 times 2 times 3. So we could group 4 times 6, which is 24, or any way you like to do it. Maybe you like to do 2 times 2 times 2 is 8, and 8 times 3 is 24. Or maybe you like to do 2 times 2 is 4, times 3 is 12, and then 2 times 12 is 24. So there's lots of interesting ways to do this. After 15, we get 16, but 16 is the same as 4 times 4, which is 2 times 2 times 2 times 2. And we don't have enough 2's to make the 16, so there will be no 16 factor pair. After 16, we have, I'm just going to put x's through these. There's no 16. 17 is a prime number, and it's not one of the factors, so that won't work. And then we have 18, which is equal to 2 times 9, but 9 is 3 times 3. And we do have 2 times 3 times 3, so we have to squeeze in an 18 here. So 18 times 2 times 5 is 10, times 2 is 20. 19 is prime and not one of our factors, so it doesn't show up with a factor pair. 20, we're really running out of room here. 20 is equal to 2 times 10, which is 2 times 2 times 5. And we have a 2 times 2 times 5. So if we group that, 2 times 2 times 5, we're left over to multiply 2 times 9, which is 18. So we have 20 times 18. Let's write that here. Sorry, I'll write it here. 20 times 18, but we notice that that's now flipping around on a factor pair we already had, so we don't count it twice. And now we're done. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 factor pairs. So I'm just going to put, I'm not going to actually write them out again because I have them in the circle. The number of factors, well, there are no numbers here that are repeats inside here. It doesn't say 18 times 18, so it's simply going to be 1, 2, 3, 4, well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then there's 2 pairs, so 12 times 2 is 24 factors. And then the prime factorization is going to be 1, 2, 3 2's multiplied together times 2 copies of 3 multiplied together times 1 copy of 5 multiplied through the mix. Now, we could put a 1 there to indicate that there's only 1 5, but we don't typically write that because it's an automatic or default exponent. Phew, that was a big one. Let's take a look at 896. So we might not know what numbers divide into 896, but because it's even, at least we know a 2 will. So we could do some division with 2 into 896. If you happen to know a bigger number, you could try that first. We could try a 6 or an 8, maybe that would work. We could try a 4, that might be easier. Let's try a 4, see if we get a whole number with no remainder. 4 divides into 8 2 times 4 is 8, and when we subtract we get 0. 4 divides into 9 2 times, because we get up to 8, but then we have a remainder of 1, and then 4 divides into 16 4 times. So far we know that 4 times 224 is equal to 896. But we also need to take the 224 and factor it. So 896 so far is 4 times, I like to put my smaller number first, 4 times 224. Now we could try dividing 4 into 224 again. Well, not again, but using 4 again, this time into 224. So 4 divides into 22, it goes 20, it goes up to 20 and it goes 5 times. So we have a remainder or a difference of 2, and then 4 goes into 24 6 times with no remainder. So I'm going to take the first 4 that we had over here, I'm just going to make that a red 4, and that factors into 2 times 2, and then this 4 over here times 56 gives us 224. So 4 times 56, and I still have a times in between. So 2's are prime, so I'm just going to copy them down with a single branch in our factor tree, and then the 4 is 2 times 2, and 56 is one of our times tables, it's 7 times 8. There are other ways you could break it up, but I like single-digit factors as much as possible. So 2 times 2 times 2 times 2, 7 is prime, and then 8 is not prime, but I happen to know that it's a perfect cube, and it's 2 cubed. So I can immediately skip going from 4 times 2 into its prime factors. This is really messy, so I want to count, because there's so many 2's, so I'm just going to count them. 1, 2, 3, 4, 5, 6, 7 2's. So 7 copies of 2 multiplied together has a shorthand notation of 2 to the exponent 7, and then we're multiplying by this 7 here. Okay, so we have the prime factorization. We know that 896 is equal to 2 to the 7 multiplied by 7. Okay, so let's give us some new space. Get rid of that, get rid of that, and I'm going to get rid of all of those green marks and put this, I'll get rid of that, and group this over here. Okay, so now we want to make our factor circle, and maybe we need to make this smaller if 360 is any indication. So, and I'm going to make my spokes of my circle a little bit further away. So we know 1 times 896, we know 2 times something, 2 times, well, it's going to be all of this, which is 1, 2, 3, 4, 5, 6 2's, and 2 to the 6, or 6 2's multiplied together is 64, and we have to multiply that by 7, so 2 to the 6 times 7 is 64 times 7. We could do that with a box method, and we get 7 times 60 plus 4. So 7 60s are 420, and 7 4s are 28. So adding all that together gives us 448. So 2 times 448. We know there won't be any 3 times because we don't have a factor of 3. But we will have a factor of 4 because we can group 2 2's together as a 4. So when we do that, This 4 could be 2 2s, then we have 1, 2, 3, 4, 5 2s. And 5 copies of 2 multiplied together is 32. This comes from our powers of 2 table. And 2 to the 5 times 7, because we still have a 7 with these 5 2s, is going to be 32 times 7. So I'm just going to adjust this now. I'll reuse it. So instead of multiplying 7 and 64, which I did earlier, 7 times 32 is 7 times 30 plus 2, and 7 times 30 is 210, and 7 times 2 is 14, and adding those together gives me 224. So 4 times 224. We know that 5 won't be a factor because this number does not end in a 5. 6 cannot be a factor because we don't have a factor of 3 to multiply by the 2 to get a 6. 7 is a factor because we have a factor of 7 here. And I am just going to make this a bit smaller. In fact, oh, that all wants to be grouped together with that. So if I group all that, get it out of the way, I notice that I've already said 7 times something, 7 times 32. So we skipped 5, 6, and 7, and we have 7 times 32. And then we can try 8, which is going to be 3 copies of 2. And 3 copies of 2 multiplies by 1, 2, 3, 4 2s times a 7. So 4 2s times a 7, all multiplied together, gives me 16 times 7. And I can reuse my box diagram to show 7 times 16. Here's the 7, and the 16 is 10 plus 6. So we get 70 plus 42 for a total of 112. So 8 multiplies by 112. 9 times something won't work because 9 is 3 times 3, and I didn't have a 3 times something, so I can't have 2 3s as my factors. 10 won't work because I don't have a 5. 11 won't work because I don't have an 11 prime factor. 12 won't work because 12 is 4 times 3, and I don't have a 3 as a factor. 13 is prime, but not one of our prime factors. 14 will work because 14 is 2 times 7. So let's try 14 times something. So 14 is going to be 2 times 7, and the remainder is going to be 1, 2, 3, 4, 5, 6 copies. So 14 times 6 copies of 2 is 14 times 64. But we already came up with, oh no, we haven't seen that one yet. So 14 times 64 is one of our factors. Okay, I'm going to create a little bit more space here because it's getting a bit crowded. And after 14 we try 15, but 15 is 3 times 5, and we don't have any 3s or 5s. After 15 comes 16, and 16 happens to be 4 copies of 2 joined by multiplication, and we do have 4 copies of 2 to play with. So I'm going to circle those together, and that's a 16 multiplied by whatever's left here. So let me move my 4 times 64 to create a bit more room for me. So now we're trying 16, which is going to be 16 times all of this. So we're going to get 2 times 2 times 2, which is 8 times 7 is 56. So we get 16 times 56. After 16 comes 17, but that's a prime number and doesn't show up here. Then we have 18, but 18 is 2 times 9, and 9 has factors of 3, which we don't have. After 18 comes 19, which is a prime number, not one that we have. And then we have 20, but 20 is 4 times 5, and there's no factor of 5. 21 is 3 times 7. We have a factor of 7, but we don't have any 3s. 22 is 2 times 11. We have a 2. We have lots of 2s, but no 11s, which is prime. 23 is prime, which we don't have. 24 is equal to 3 times 8. 8 is a bunch of 2s, which we have, but 3 doesn't show up. 25 would be 5 times 5, and we don't have any 5s in our factoring. 26 is 2 times 13, and we don't have any 13s. 27 is 3 cubed, and we don't have any 3's, let alone 3 copies of 3, joined by multiplication. I think I'm going to remove this box here so I have some more room. After 27 comes 28, which is 4 times 7. Well, we don't have any 4's, but we do have 2 2's. So this is 2 times 2 times 7, which we do have. So we need to find a factor partner for 28. And we're going to have 1, 2, 3, 4, 5 2's left over. And so we have 28 times whatever 5 copies of 2 is. And from our powers of 2, we're starting to recognize that that's 32. These numbers are getting closer together, which means we're almost reaching our wraparound point. After 28 comes 29, which is prime, which we don't have. Then 30, which is going to be 3 times 10, or 6 times 5, or 2 times 3 times 5. But we don't have a 3, so we don't have a 30. Then 31 is prime, so we don't have it. 32, well, we know 32 is 5 copies of 2. We just talked about that. In other words, it's 2 raised to some exponent. 32 is a power of 2. It's the 5th power of 2. So then 32, which we have, because we've got 5 copies of 2, we've got 4 of them over here, we've got 1 of them over here, and then the remaining factor is going to be whatever 4 times 7 is, which is 28. And this is good news because now we've got a repeat, and so we can stop. And so we circle our factor pairs, and that's the answer for part 1. These are not factor pairs, this is a factor pair. And then we see that we've got 1, 2, 3, 4, 5, 6, 7, 8 factor pairs, and inside each pair the numbers are all different. So 8 pairs of 2 numbers each is 8 times 2, which is 16 factors. Phew, we've done it. Now that we have some practice and experience with our factor pairs, we're going to use them to come up with things called the highest common factor and the lowest common multiple. So let's consider 60 and 70 and come up with their prime factorizations. 60 is 6 times 10. There are lots of ways that you could start unraveling this, but I find this one easy because of the ending in a 0. So 6 is 2 copies of 2, so 2 copies of the base number 2 multiplied by 1 copy of 3 and 1 copy of 5. That is our prime factorization for 60. And then 72, if you know it as a product of single digits, that's helpful, and so it's important to memorize the single digit times tables. So 8 we can break apart. Maybe you know that 8 is 3 copies of 2 joined by multiplication, and 9 is 2 copies of 3. So 72 is going to be 3 copies of the base number 2 multiplied by 2 copies of the base number 3. 2 cubed times 3 squared. And every time you see the word or hear the word cube, think of a 3-dimensional cube, and when you hear square, think of a 2-dimensional square. So 72 is equal to 2 cubed times 3 squared. And then what are the prime factors that are common to both? Well, it may be helpful actually to expand these. So I'm just going to write the blue underneath, 2 times 2 times 3 times 5, and I have room to put the red expanded to the side. So 2 times 2 times 2 times 3 times 3. So I'm just going to, in green, cross off each one that's common and then write it over here. So I have a 2 common, I have a second 2 that's common, but I don't have a third 2 that's common. I have a 3 that's common, and I don't have a 5 or any more 2's. So that's it. These are the prime factors that are common. Now, it didn't ask me to multiply them. I put a times in between. It just asked me to list them. So the prime factors are 2 squared and 3. So I'll leave it like that. So I want to know what the greatest number that divides into both numbers is. So what's the biggest number that will go into 60 evenly as well as going into 72 evenly? This number has a name. It's called the highest common factor. Both numbers can be divided by 2. Can they be divided by anything bigger? So this is interesting. Let's take a look at a calculator just to understand a bit better. On this calculator, this dot means multiplication. If I just show you 2 times 7, it gives 14. So we found that the prime factorization of 60 is 2 squared times 3 times 5, and the prime factorization of 72 is 2 cubed times 3 squared. We also found that they have 2 2's and a 3 in common. This has an extra 3 and an extra 2, whereas this has an extra 5 that this doesn't have. So these are the only factors in common. And when we multiply those together, we get 12. So what we're finding is that if we do 60 divided by 12, we get a whole number, and that whole number is 5. Likewise, 72 divided by 12 gives us a different whole number, but that means that 12 divides both into 60 and 72. There is no bigger number than 2 times 2 times 3 that will divide into 60 and 72. So what that means is the highest common factor, or the biggest number that will divide evenly into both numbers, the HCF, is the product of these common factors, 2, 2, and 3. And so 2 times 2 times 3 is the HCF. So I might write it as the HCF of 60 and 72, or I might just write it in words, the HCF of 60 and 72 is 2 times 2 times 3, which is equal to 12. Now, this is the highest common factor, the largest number, the greatest number that divides into both 60 and 72. Now, we're looking also at something different, the first or the smallest multiple, the first multiple that appears in both of their times tables, and that's called the lowest common multiple. Sometimes the L in LCM stands for least or smallest common multiple. So if we were to write the times tables out for 60, we would do things like 60 times 2 is 120, 60 times 3 is 180, times 4 is 240, times 5 is 300, times 6 is 360, times 7 is 420, and I'm running out of room, but it would go on. Similarly, 72 times 1 is 72. If we double it, we get 144. If we triple it, that would be the same as adding 3 copies of 72 together. So we could add another 72 to this and get 216. We could add another 72 to this and get 288. We could add another 72 to this. Now I might write it down underneath. I get 290 plus 70 is going to be 360. And I could add one more, 360. And if I add another 72 to that, I'm going to get 432. 432. And so these numbers go on. But the first common multiple is the first multiple that's common to the blue list and the red list. And that first common multiple, let me highlight it with the same color, is 360. So 360 is our, it says HFC because I did a copy paste here. Let's just change that because we are now working out the LCM of 60 and 72. And it's equal to 360, but we want to find a faster way of coming up with this number instead of writing out the blue list of multiples of 60 and the red list of the multiples of 72. I'm just going to write those in words above here. Multiples, like the times tables, of 60 and 72. So how can we use the factors of 60, the prime factors of 60 and the prime factors of 70 to come up with this number? Well, the 360 is going to be a product of all of the factors. So the lowest common multiple, what I'm going to do is write down all of the factors of either the blue number or the red number. And I guess I'll do the blue number because it comes first. So I have 2 times 2 times 3 times 5. Now I'm going to take a kind of inventory of my red factors. I'm just going to write my red factors again expanded. 2 times 2 times 2 times 3 times 3. So I need a 2. Do I have one? Rather, I'm going to try to introduce the red factors to the lowest common multiple. I need a red 2. I already have one, so I don't need it. I need a second 2. I have a second 2, so I don't need that one. I need a third 2. I don't have a third 2, so I need to multiply by another 2. That guarantees that I have enough 2's for the red, and I have more than enough 2's for the blue. So I put my third 2 there. Now I need a 3, but I already have one 3, so I don't need this 3. I need a second 3, which I don't have, so I need to multiply by a second 3. And so this number, when we multiply it all out, will give us 360. Let's just double check. We can group nicely together. I'm going to put the 2 and the 5 together as factors, and then maybe 2 times 3 and the other 2 times 3. So 2 times 3 is 6, times another 6 is 36, and then 36 times 10 is 360, which is the first common multiple of both times tables for 60 and for 70. So we will say that the lowest common multiple of 60 and 72, I think I said 70, 72 is the number 360. So this is a very nice systematic approach that you can take from the prime factors to figuring out two important numbers in dealing with patterning: the highest common factor and the least or lowest common multiple. Here we are asked which number is larger, 10 cubed or 30 squared. 10 cubed we know means 10 times 10 times 10, or 10 times 10 squared, because that's one copy of 10. That's two copies of 10, all of them being joined by multiplication. And 10 times 100 is 1,000. 30 squared, it's kind of like thinking of a square where all the sides are the same and multiplying 30 times 30 to get the area. And the area of a square whose length is 30 is equal to 30 squared. And as a standard number, that's 3 times 3 times 10 times 10. So let's just look at 30 times 30 and use a sort of, not a full prime factorization, but a part prime factorization to regroup this. I can now group the 3 times 3 together, mostly because I want to group the 10 times 10 last. And 3 times 3 is 9, times 10 times 10 is 100. So 30 times 30 is the same as 9 times 100, which is 900. And so the area of this square, if the lengths are both 30, is 900. Okay, so just looking at multiplication in more visual ways that we can understand or make it easier for us to work out. So that's a factor tree method, and this is just representing the area of a square with length 30. So we see that this number is bigger, and the question of by how much means to subtract. So 1,000 minus 900 is 100, so 10 cubed is bigger than 900, than 30 squared by 100. The last question is giving us lots of practice working with prime factorization, as well as the highest common factor and the least common multiple. So we will do a couple together. 24 is 3 times 8, or 4 times 6, or 2 times 12. And 8 is 2 cubed, so we know that 24 is equal to 2 cubed times 8. Then the second number, 30, is equal to 3 times 10, and 10 is equal to 2 times 5, so altogether we have 30 is 2 times 3 times 5. So we have our prime factorizations, and now we can set off finding the highest common factor and the least common multiple. So the highest common factor is the product of the common factors. So the common factors, we have 3 2's here, we only have 1 2, so there's only 1 2 common. My apologies, I put an 8 here and I meant to copy that 3 down in the place because the 2 cubed is an 8 already. So this should say 2 cubed times 3. So let's write this in expanded form. I think sometimes the expanded form might be easier to see the patterning here. So 2 times 2 times 2 times 3. And we have 1 2 in red, we have 3 2's in blue, so what do we have in common? Just 1 2. We have a 3 in blue and we have a 3 in red, so it is common. We have a 5 in red but not in blue, so 5 is not common, and the highest common factor will be 6. What this means is that 6 is the biggest number that divides evenly into 24 and 30. 6 is the largest or the highest or the greatest. Sometimes this is called the greatest common factor. Greatest common factor. It's the greatest or highest factor that divides into both. That's where the word common comes from, into both 24 and 30 and 30. So we know 6 will divide into 24 4 times, and 6 will divide into 30 5 times. So that's the greatest or highest common factor, and the next thing we want to do is work out the LCM, the least common multiple. So the LCM is going to be a product not of just the common factors, but the product of all factors. So in order to do this one, I like to write down all of the factors from one number or the other. So I'm going to write down all of the blue factors. Then I'm going to take an inventory and see who I already have, and I won't include it as an extra for red. But if I don't have it, I need to introduce by multiplication. So do I already have a 2? Well, in fact, I have 3 2's, so definitely I have a 2. Do I already have a 3 as a factor? Yes, there's 1 3 there, so I don't need to introduce another one. And do I already have a 5 as a factor? I don't, so I need to multiply by a 5 to get the LCM. And so when I multiply this together, doing it creatively, I'll group the 2 times the 5, which is 10, and then I have 4 times 3, which is 12, and 12 times 10 is 120. What this means is that 120 is the first number common to the times table, to both times tables, common to the 24 times tables, or times table, and the 30 times table. Okay, so we can practice this with the other numbers. I think coming up with the meaning each time would be really helpful. Okay, so let's take a look at the next one. So in part B, I'm going to make the first number be my blue number and the second number be the red. They both end in 5, so I know that 5 can divide evenly into each number, which means that 5 is a factor. 5 goes into 16 3 times with a remainder of 1, and then 5 goes into 15 3 times with a remainder of 0. So 165 is going to be 5 times 33, and 33 is 3 times 11. So I have 5 times 3 times 11, or if I like to order it from smallest to largest, I could do it that way. And so I can say that 165 is equal to 3 times 5 times 11 in prime factors. Then I can do a division by 5 for 385. And 5 goes into 385 7 times, because 7 times 5 is 35, with a remainder of 3. And then 5 goes into 35 7 times. So 385 is 5 times 35, and 35 is not prime, so it factors into 5 times 7. So we can see that 385 is 5 squared times 7, or 2 copies of 5 multiplied together with a 7. So for now, I'm not going to write my prime factorization with exponents, because I really want to be able to count each factor carefully. Maybe I'm just going to put a box around those so it's easy to see them, because I've got a lot happening here. So there's my prime factorization, and the next step then is to come up with the highest common factor, which is the product of the common factors. So let's just take inventory one by one. I'll write it over here. HCF is equal to, well, do I have a 3 factor that's common to both? I have a 3 here, but not here, so it's not common. What about 5? 5 is here, and I have a 5 here, so there's 1 5 common. Then I have an 11 here, but not over here, so 11 is not common. I had 1 5, but not a second 5, so it's not, a second 5 is not common. And I have a 7 in red, but not in blue, so a 7 is not common. So I only have one common factor, and the highest common factor is 5. What that means is 5 is the biggest number that divides into each 165 and 385. Now we're going to do the second process. I don't want to highlight that because I can't see it's blue. We're going to do the second process now for the lowest common multiple, or the least common multiple. So unlike selecting the factors that are common and multiplying them together, we're going to select all of the factors but without any repeats. So the lowest or least common multiple, I'm going to write down all the factors from one of the numbers. So I'll take the first number in blue and write it out. And then I'm going to take any additional factors that we don't already have from the red number. So we need a 5, but we already have a 5, so we don't need that one. We need a second 5, and we don't have a second 5, so we need to multiply that. We also need a 7, and we don't have a 7, so we need to multiply by a 7. And then the answer to all of that is the least common multiple. So this can be pretty messy to multiply. Nobody said we had to expand it, but if we did, we could expand it by hand or with a calculator. I'm going to multiply it partially. So the lowest common multiple is going to be 5 times 5, which is 25, and then times 3 is going to give me 75, and then 11 times 7 is 77. So 75 times 77 is my least common multiple. We can just work that out with a calculator. 75 times 77, and we get 5,775. That's a palindrome number because reading it forwards and backwards is the same. So 5,775. So if we were to write out the times tables for 165 and another times tables for 385, the first number that would be in common to both times tables is 5,775. Okay, let's try the next one. The first number is in blue and the second number is in red. Well, they are already prime numbers, so we can't factorize them any further, and so we're ready to find the highest common factor and the least common multiple. So the highest common factor is going to be any common factors. So the key word here is common, whereas in the next case the key word is all with no repeats. So we are going to look for any common factors. Here there's a factor of 3, but not over here in red. Red has a factor of 5, but not over here in blue. So technically the only factor that they would have in common is an automatic 1. So I am just going to write down that the highest common factor, because they have nothing in common, is equal to 1. So that's the biggest number that will divide into 3 and that will divide into 5. Now we want to come up with the least common multiple, which is a product of all of the factors. So we need all the blue factors and all the red factors with no repeats. So we need a 3, and that makes sure that we've taken care of all of these factors, and we need to multiply by any additional factors over here. We don't already have a 5, so we need to multiply by it, and 3 times 5 is 15. What that means is 15 is the first number that both 3 and 5 have in common in their times tables. Okay, let's take a look at the next example. In part D, we're given 4 numbers, so we're going to have to do 4 prime factorizations. So the first number is 2, and then 4, and then we have 2 more numbers. So I'll just copy this. And 6, and then 8. Okay, so I'll make 4 different colors here just to keep track of everything. So let's change this to a different color. We can pick any color we want. I think I will pick orange, and then I'll pick a different color over here. And I will pick, I guess, black. Okay, so the prime factorization of 2, well, 2 is already prime, so it's done. The prime factorization of 4 is 2 times 2. The prime factorization of 8 is 2 times 2 times 2. And I'm just going to move that over a little bit. And then the prime factorization of 6 is that orange? 2 times 3. And so the highest common factor is going to be the product of all the factors that are common. So is there any factor or more than one factor that is common to all of them? Well, since we know that blue only has one factor, then there can't be more than one common factor. So the only common factor is 2, and that's what our highest common factor is. This is the biggest number that will divide into blue, red, orange, and black. Now, the lowest common multiple, or the least common multiple, is going to be a product of all the factors with no repeats. Since I don't want to deal with repeats, I might start off listing the factors for the number who has the most factors, and that number is 8. So I'm going to put all of 8's factors down. So now I know that I have kind of accounted for each of these factors. Now I move on to somebody else. According to 4, I need a 2, but I already have a 2. I need a second 2, and I have a second 2. So I don't need to introduce any more, because the factors of 4 were already more than enough for the factors of 8 were more than enough than we needed for the factors of 4. So we move on to 6. I need a 2, but we already have a 2. And we need a 3, but we don't have a 3, so we need to join it by multiplication. So I'll multiply by 3 here, and then cross it off. And then we come to the 2. I need a 2, so does that mean I multiply by 2? Well, no, because the no repeats means if I already had one sitting there, I don't need to put another one there. I don't need 4 2's in any of these numbers. The most I need for any number is 3, so this blue is a repeat. And so this would be my lowest common multiple, or least common multiple, which is going to be 8 times 3, which is 24. And that would be the first number that occurs in the times tables for 2 and 4 and 6 and 8. Now part E looks a little scary, but actually we realize that the first number has already been given in prime factored form. So 2 to the 4 times 5 cubed, this is nice because we know that we've got 4 copies of 2 and 3 copies of 5 joined by multiplication. So that's already been done for us. The second number is also in prime factored form, and I'm not going to have enough room here, I'll just put it here. 2 cubed times 3 squared times 1 5 times 1 7 is going to be 3 copies of 2, 2 copies of 3, and a 5 and a 7. So I'm putting it in both exponent notation as well as expanded notation. Okay, so the highest common factor is going to be a product of any of the common factors. So we're going to go one by one. And I'll cross them off as we go. I have a 2 common to both. I'll do the highest common factor in black. So I have a 2 common to both, so I write that down. I have a second 2 common to both, so I'll multiply by a second 2. I have a third 2 common to both, so I'll multiply by that. But I don't have a fourth 2 common to both, so I won't put that 2 here. Now, do I have a 5 common to both? Yes, I do. And so I'll multiply by 5. Do I have a second 5? No. And a third 5? No. And then over here, I'm missing a 3 and a 3 and a 7, but they're not over here. So I have found all of the common factors. And when I multiply 8 times 5 or 10 times 4, we get 40. This means that 40 is the biggest number that will divide into the blue number and into the red number. So now I'm going to take off all of these tick marks because they will get in my way for when I'm finding my least common multiple. So the highest common factor is the product of the common factors, but the least common multiple is the product of all the factors with no repeats. So we are going to go and take inventory again. To find the least common multiple, start by writing all of the blue or all of the red factors. You might put the one that has more factors, and I think that's red. So I'm going to start with this because then I have probably less to introduce than if I had started with the fewer factors. So now I've got this one, this one, this one, this one, this one, this one, and this one because I copied it directly. 3 2's, 2 3's, 1 5, and 1 7. So now we come over here. I need a 2, but I already have a 2. So I can kind of cross them off as I go along. I'll take the crossings off. I need a second 2, and I have a second 2. I need a third 2, and I have a third 2. I need a fourth 2, but I don't have a fourth 2, so I need to multiply another 2. And I've run out of room here, but I'll put it underneath. So now I have another 2. I need a 5, and I already have a 5. I need a second 5, but I don't have one, so I need to multiply. And I need a third 5 that I don't have, so I need to multiply another 5. The 3 and the 3 and the 7 were uncommon factors from the red, and the extra 5s and an extra 2 were the uncommon factors for the blue. So we will have 4 2s, but we won't have 4 plus 3 making 7 2s altogether. We just have 1, 2, 3, 4 2s. So that's why we have no repeats. We have 1, 2, 3, 5s, 1 5, 2 5s, 3 5s, but we don't add this fourth 5 to make a total of 4 5s. We don't need the repeats. Okay, so then we just creatively combine these factors so that we can multiply easily. That means I want to put 2s and 5s together. So I'm going to put a 2 and a 5 together, another 2 and a 5 together, and another 2 and a 5 together. So that gives me 3 copies of 10, which is 1,000. And then I have, for the LCM, 1,000 times 2 times 3 times 3 times 7. So maybe I group these together. 2 times 3 is 6, and 3 times 7 is 21. So 6 times 21 times 1,000, and 6 times 21 is going to be 126. And so the LCM, which I'm running out of room for, is 126 times 1,000, which is 1, 2, 6, 1, 2, 3 zeros. So 126,000. Okay, one more to go. We have 3 factors or 3 numbers here, so I'm going to copy another one of these and change its color so we can keep track of the numbers by color. I think this time I will choose green. And so the prime factorization of the first number is going to be of 32, then the second number in red is 48, and then the green number will be 96. Slightly different greens. Okay, so 32 is one of the powers of 2, so 32 is 5 copies of 2 multiplied together, so 2 times 2 times 2 times 2 times 2, lots of 2's. 48 is 6 times 8, which are single-digit factors, which are important for us to memorize, and 6 is 2 times 3, and 8 is 3 copies of 2, all joined by multiplication. So I could reorder them. I could put all the 2's first and the 3 second, but you can leave it like that. Now 96 is actually 2 times 48, so I'll just write 96 over here. 2 times 48, which is going to be another 2 on top of all of these. So I had 1, 2, 3, 4 red 2's, so I will have 5 green 2's plus the 3. Or in addition, as well, we have another 3. And so now we have the highest common factor, which is going to be the product of the common factors. Well, we have a 3 in the red and the green, but not in the blue, so 3 is not common. We have 5 2's in the blue. We also have 5 2's in the green, but we only have 4 2's in the red, so we're going to have 2 to the 4, which is 16. And the LCM is going to be the product of all the factors with no repeats. So in the first blue, we have 5 copies of 2. In the red, we have 4 copies of 2, so we already have enough. We don't need to introduce any more, but we need a 3. And in the green, we need a 3, which we already have, and we also need 5 2's, which we already have. So the LCM is going to be 2 to the 5 times 3, or 32 times 3. And 32 times 3 is the same as 3 times 32. So you could add 32 to itself 3 times, 3 of 32, or you could multiply the 3 and the 2 to get 96. So there you have it, different ways to work with whole numbers, their prime numbers, their prime factorization, their powers of 2 and 3 we've been using a lot. We've been looking at square numbers, cube numbers, and now we've been looking at the highest common factor and the least common multiple. It's really worthwhile knowing your times tables and your special number sequences, like the perfect squares and the perfect cubes, because then it helps you to work with numbers, to see the patterns, the relationships, and to grow in your mathematical ability as you study further along. Thanks for watching the video.